In this section, we're going to be going over the definite integral again and area under a graph. So starting here with area under a graph, we're going to be solving the area problem, which is going to consist of us finding the area of a region under the curve on an interval from a to b. So if f of x is a continuous non-negative function on the interval a to b, we're going to refer to the area of this region shown down here. So this shaded in region, we're going to refer to that as the area under the graph or the area under the curve from a to b. So you can see here we have our function, we have our graph, our curve right here, and the interval, the x values are from a to b, and you make these vertical lines that go up to the function, and the area is just going to be that shaded in region from the x-axis up to the function itself. Okay, so we're going to be finding that area, and we're obviously going to be doing that using a definite integral, and this is how we can do it. Thankfully, we already know how to do the math here. If we are looking for the area under the graph of f of x from a to b, it's going to equal the definite integral from a to b of that function. So we know how to just take the integral and then plug in the upper bound and then plug in the lower bound and then subtract those two results. So we actually know how to do the math here, but now we're just taking into account that what we actually get is the area underneath the curve. So let's do some examples here. Let's compute the areas using a definite integral to verify the areas given. So this first one, we have this rectangular region from, it looks like it goes from 0 to 3, and then it's a horizontal line and it goes up to 4. So we know the area here is 12 because it's a rectangle. Area equals length times width. 3 times 4 is 12. Let's do it using integration. So the integral here would be the integral from 0 to 3. So always remember that we're talking about the x values here, 0 to 3. And the function is 4. So we're looking for the integral from 0 to 3 of 4 dx. So let's go ahead and evaluate. The integral of 4 is 4x. We're going to evaluate that from 0 to 3. So we go ahead and we plug in the upper bound of 3, minus plug in the lower bound of 0. We get 12 minus 0, so we get an area of 12, which we already knew that was the answer, but we just verified it. Okay, next one, we have this, this region right here. And it is this trapezoid region, and it says that the area is 3/2, so 1.5. And we want to verify that using an integral. So we're going to take the integral x values here from 2 to 3 of the function negative x plus 4 dx. So that's our function given to us. And then we go ahead and integrate this. We end up getting the integral negative x squared over 2 plus 4x from 2 to 3. And now we have to do upper bound minus lower bound. So we plug in a 3. Negative 3 squared is negative 9. Plus 4 times 3 is 12. That's the upper bound. Plug in the lower bound of 2. Negative 2 squared is negative 4. Negative 4 over 2 is negative 2. Plus 4 times 2, we get 8. So we get negative 9/2 plus 12 minus 6. And just evaluating this, we end up getting 3/2. So that's just the verification. Once again, we got the correct answer. Next one, for C, we have another trapezoid region, and we said that the area of this whole entire shaded region is 6. Let's go ahead and verify that. So it's going to be the integral from 0 to 4, but we have two different functions over this interval. The first function is from 0 to 2, and that function is x. And then our next function is from 2 to 4. Oops, so that's going to be adding the integral from 2 to 4. And this function is 2. So we have two separate functions, but to get the total area, we're going to add them up. So the first one we integrate and we get x squared over 2 evaluated from 0 to 2. Second one we get 2x evaluated from 2 to 4. And we plug those in. And I'll leave that to you guys to verify, practice plugging those in. We should end up getting 6. And then for D here, we have the parabola, the quadratic f of x equals x squared, and it looks like we are integrating this from 0 to 1 and finding the area integral from 0 to 1 of x squared. We take the integral, that's x cubed over 3, evaluated from 0 to 1, and this is going to end up giving us 1/3. And obviously I'm kind of skipping some steps. You plug in 1, plug in 0, subtract. We should end up getting 1/3. So this area here is 1/3. Okay, next example. Let's compute the area of the shaded region under the graph of 3x squared plus e to the x from -1 to 1. So before we actually show what this graph looks like, let's just go ahead and do the math. We want the area underneath the curve, so we're going to be integrating the function 3x squared plus e to the x dx from -1 to 1. So the integral of 3x squared is going to be x cubed over 3, but if we divide 3 divided by 3, they cancel. So the derivative of, the integral of 3x squared is x cubed. And the integral of e to the x is itself e to the x. And we evaluate that from -1 to 1. We go ahead and we plug in. That's 1 cubed minus e to the first. For the upper bound, now we subtract the lower bound. -1 cubed plus e to the -1. And we need to simplify. So that's going to be 1 minus e minus -1 plus 1 over e. And I just realized that this should be a plus. So that's plus e plus e. There we go. And plug this into the calculator because it's going to give us a decimal, and it's going to be about, we have to round. It's going to be about 4.35. So let's go ahead and see what the function looks like when we graph it down here. So if you graph this, it's going to look something like this right here, and you can see the area that we just found, the shaded in region from -1 to +1, and just verifying that we got the correct answer because it's here written down for us. Okay, next one. We want to find the shaded region under the graph of x cubed plus 2x plus 1 from 0 to 1. So we want the area, so we go ahead and integrate our function 2x cubed, or x cubed, plus 2x plus 1 from 0 to 1. And we integrate that and we get x to the 4th over 4 plus x squared over 2, but when you divide by 2, it cancels with this 2 right here. And then the integral of 1 is just x. Plug in our bounds from 0 to 1, and that's going to end up giving us, let's plug in the upper bound first. That's going to be 1/4 plus 1 plus 1, and now we plug in 0. So what I like to do is, when you're plugging in 0, I like to take a look at what we're plugging into. If we plug in 0 here, every single thing is going to be 0, right? 0 over 4 plus 0 plus 0. So instead of writing that down, just recognize that and just put -0, and then you don't have to do anything else. So we end up getting 1/4 plus 1 plus 1. And after getting common denominators, we get 9/4, which is 2.25 as the area. And let's verify that down here. So here is our function. And the integral from 0 to 1 represents the area underneath the curve, between the curve and the x-axis. And right here, verified, the area is 2.25. Okay, so the next thing that we're doing in this section is Riemann sums, which is going to seem pretty complicated when we get to the notation for it. Hopefully it makes sense though. So what we're going to be doing here is we're going to be estimating the area of a region under a curve. And we're going to be doing this using rectangles. There's also other ways to do it using like trapezoids, but we're going to be doing it with the rectangle method. Okay, so let's take a look at this first right here on the left. So that is the area under the curve of f of x from a to b, and we found that by integrating from a to b, right? We were just doing that in the previous examples, and now we're going to be estimating using this Riemann sum method. So to start off here, n is going to be the number of rectangles that we're using in each approximation. So remember that because we need to use that going forward. So n is the number of rectangles that we are using in the approximation. And the ones that we have over here on the right, so all of these ones over here, are approximations of the region right here on the left. So you'll see that the one next to it, this one right here, we have two rectangles. If we shade those in, then that's an approximation for this area right here on the left. We don't know exactly how accurate it is. We can see that it's overestimating here, underestimating here, overestimating here, but that's estimating with two rectangles. The next one, we have four rectangles, and you can see once again it's not perfect. Maybe it's getting a little better because we have an over approximation, under approximation, over, under, over, and then over. So still not perfect. And then the next one is with 10 rectangles, and once again it's still not perfect, but you can kind of see as the number of rectangles we use is getting larger and larger, the closer it's starting to look like this exact area over here on the left. Okay, so let's get into what we'll actually be doing here. So given a continuous non-negative function f of x on the interval a to b, we're going to divide the x-axis into n equal subintervals. So we're going to divide it into n equal subintervals because n is the number of rectangles that we want. So these rectangle lengths, they need to be the same when we're within the same question, or else we can't really do this very accurately. So we're going to divide the interval a to b into n equal subintervals. These subdivisions, we call them partitions. And if we're trying to divide a interval into n equal parts, to figure out the length of one part, you need to divide that interval length by n. So for example, let's say we had, before we take a look at this little definition, let's say we had the interval from 2 to 12, and let's say we want 5 rectangles for this region. We want 5 rectangles. That means we need to chop up this interval in 5 equal parts. So that means we need something like this, where it looks like this. So we have 5 equal parts, right? We have 1, 2, 3, 4, 5. The question is, what are these numbers going to be? And what is going to be the width, one of these widths from one number to the next number? So what we would have to do here is we would have to do 12 minus 2 and get the length of the region, which would be 10. And then we would need to divide that 10, the length of that interval region, divided by the number of rectangles that we want, which would be 5. So that would give us 2. So that means we would have to add 2 to each little partition here to get the next value. And now we just successfully chopped up that interval from 2 to 12 into 5 equal regions. And we're going to be using those regions to create our rectangles. So the way that we do this, the way that we find the width of one subinterval is exactly what we just did, is we're going to call that width delta x. And that delta x is going to be the upper bound on our interval minus the lower bound divided by how many rectangles we want. So we're pretty much going to be doing this every single time for each question. And it's going to be one of the first steps that we do. So before we get into actually doing our own problem, let's get a little bit further into what we're going to be doing. So let's say in each subinterval, let's select any point in each subinterval. X sub 1 is going to be the point in the first interval. X sub 2 is going to be the second subinterval point, and so on. These points are going to be used to form rectangles that approximate the region under the graph. So let's look at this graph right here that's drawn. We have the curve f of x, and we have these subintervals. We have an interval from here to here, and then from here to here, and then it keeps on going. We just didn't fill them all in, and then it ends with that one. Those are all the same width. They have all the same delta x. So what we said is we're going to select some x value in each little subinterval, and that is the x value that we use to find the y value where the function is at that point. So you'll see that it goes up to where the function is, and from that point we create a rectangle. So for the first one, we go up that high, over, and then back down. And we do that for each and every one. And then what we do is we find the area of each rectangle, and then we add them all up, and then that's our approximated area. The reason why we can do this is because it's super easy to find the area of a rectangle. It's just length times width. So the area of the first rectangle, well, instead of length times width, I'm just using height times width. The area of the first rectangle is the x value, which should actually be, this should be written as delta x. This shouldn't be x1. Let me fix all these. There we go, that's better. It is the x width. It's the x width times the y value at that point. So it's just height times width, where the height is the function evaluated at the x coordinate in the subinterval, and all of the widths are the same. Remember that delta x we found on the last page. It's the interval length minus how many rectangles we wanted. Okay, and once you know this, you know how to do all of them. The second rectangle that we make is going to be that delta x times the function value of that x coordinate that we chose, and then so on. We keep doing that for however many rectangles that we have. Okay, so what we do is we construct n number of rectangles, and we can add up each one of those areas together for however many rectangles we have, and this is called the Riemann sum, and this gives us an approximation of the area under the curve over a specified interval. So the way that I like to write it, and that I'm going to be writing it, is this way right here. What we did here was we factored out the delta x, because that's the width of each one of these rectangle areas. So instead of doing it all those times, you can just factor it out and then multiply all the heights added together. Okay, so I'm going to be using this version of it when we do the problems. Okay, let's see an application type example first. To estimate the area of a 100-foot wide waterfront lot, a surveyor measured the distance from the road to the waterline at 20-foot intervals. and they did this starting 10 feet from one corner of the lot. Use this data to construct a Riemann sum approximation to the area of the lot. So we have this waterfront lot from 0 to 100. It's a 100-foot lot. And we have this water's edge up here. So what we really want is this area from the water down to the road. But instead of actually finding the exact area, what we're going to do is we're going to approximate it using this Riemann approximation, this Riemann sum approximation, using the sum of rectangles. So we chopped it up. We chopped up that area into 20-foot subintervals. And then from these subintervals, we took the midpoint from all of these subintervals and used that midpoint to find that distance away from the waterfront. And then we created rectangles for each one, found the areas for each rectangle, and now we're going to add them up and get our estimated area. Okay, so the Riemann sum approximation, we have 5 different rectangles. So the Riemann sum approximation is going to be the function evaluated at the first one times delta x plus the function evaluated at the second one times delta x plus the third one, fourth one, and the fifth one. And like we said, we could do it this way and plug in all of our values, but I mentioned that I like to factor out the delta x. It makes it a little bit cleaner. So factoring out the delta x, we're going to be left with all of these values. Remember that these are the heights of the rectangles, and we had 5 of them. And now we can just go ahead and plug in. So our height here is 20 because that is the width of each subinterval is 20. That was given to us. So that's going to be 20. And then all of these f of x's are going to be the heights. So we have all of these different heights here. We have 39, 46, 44, 40, and 41.5. Those are the heights of each individual rectangle. So let's write those in. And let's go ahead and add them all up. So 20 times 210.5. And we apply those two together and we get 4,210 square feet. So this is an area approximation, so it should be in square feet. You could label it feet squared like that if you want, however you want to do it. And I leave out units when I'm actually doing the math, but you should have known that 20 was in feet, 210.5 was in feet. Foot times foot is foot squared, so that's another way you knew it was feet squared. Okay, so this area is approximately 4,210 square feet. Probably a little bit off because it's an approximation, but it seems like a pretty decent approximation. And all it is just adding up a whole bunch of areas of rectangles. So next example, let's use a Riemann sum approximation with n equals 4. So we know that we want 4 subintervals, we want 4 rectangles. To estimate the area under f of x equals x squared from 0 to 1. And we want to select the right endpoints for these intervals for x1, x2, x3, x4. So there's 3 things that I like to kind of have written down all at the beginning here. One thing is the formula, second thing is the graph, and the third thing is a number line to figure out our width value delta x. So here is our formula that I wrote down there. That's going to be the Riemann sum approximation, f of x1 times delta x plus f of x2 times delta x, and so on. And we have, there should be 4 of them. I accidentally put 5 of them. So there we go. That is our approximation that we're going to be using with our formula. And now let's take a look at what we're actually doing. So anytime you can graph something out, I recommend doing that. So the 0 is at the origin, and then let's let this be 1 over here. The graph for y equals x squared is a parabola, and then only looking at the right-hand side, it's going to look something like that. So we're trying to find an approximation for this area in here, right? But we're not going to find it exactly. If we wanted it exactly, we could find it by taking the integral from 0 to 1, but we want it using rectangles. So we want 4 rectangles. So I just chopped it up into 4 equal subintervals, and we're using the right endpoint for each one. What that means is we use the right endpoint tells us the height of the rectangle. So there's one right endpoint. Here's another right endpoint going up to the curve. Here's another one, and here is another one. So we're going to be finding the areas of those rectangles, and we're going to be adding them together. So now the question is, how do we figure out what these x values are down here? And this is the other third thing that I mentioned with the number line. We want to go from 0 to 1, and we need 4 subintervals here. So what are those numbers? Hopefully it's kind of obvious because the numbers are pretty nice right now, but what we would have to do here is find delta x, which we know is b minus a over n, which we know is 1 minus 0 over 4, which is 1/4, or 0.25. So that means we're going to be adding 0.25 over and over and over again. So adding 0.25, we get 0.25. Add another 0.25, that's 0.5. Add another one, 0.75. And add the last one, that gets us to our endpoint of 1. Okay, so we have 4 equally sized intervals now that are going to represent the x's for our rectangles. And using the right endpoint, that's going to represent this value, this value, this value, and this value, the right endpoint of each one. So that actually tells us exactly what we have now. We're using 0.25, 0.5, 0.75, and 1 as our x1, x2, x3, and x4. So we could have done the left endpoints. If we did the left endpoints, we would have been using 0, 0.25, 0.5, and 0.75. So let's go ahead and do our Riemann sum approximation now. Let me just move all of this down. And what I'm going to do now is I'm going to factor out that delta x. So we're going to factor that out. That leaves us with f of x1 plus f of x2 plus f of x3 plus f of x4. And let's actually plug in everything that we know so far. Delta x is 0.25. F of x1 was 0.25. So f of 0.25. F of x2 was 0.5. x3 was 0.75. And x1, or x4, was 1. So what we have to do is we have to find out those y values for each individual one. And I'll start that on the side. We need f of 0.25. F of x was x squared. So 0.25 squared, we get 0.0625. And then we do the same thing for all of them. 0.5 squared, we get 0.25. and f of 0.75 is 0.5625, and f of 1 is 1. Now we go ahead and we plug all of those in. So 0.25 times, and we're going to add all of these up. And then we are going to multiply them by 0.25, and that's going to be our area approximation. So adding all those up, multiplying by 0.25, we get about 0.46875. So that is the approximation for that area. And let's go ahead and actually find the actual area just to compare. And we do that by integrating from 0 to 1 of our function, which is the integral ends up being x cubed over 3 from 0 to 1. Plug in the upper bound, plug in the lower bound, and subtract. We get an actual area of 1/3, which we know is about 0.333 repeating. So we can see that our answer, our approximation, was an overestimate. It was just a little bit more. And you can tell that it's going to be an overestimate because of all of these little chunks that we had extra that are actually not part of the area under the curve. Okay, let's do one more here. So we're going to be doing essentially the same thing, finding a Riemann sum with n equals 10 to estimate the area under y equals x squared again from 0 to 1. Instead of right endpoints, I'm going to change this to left endpoints. And we're going to use those left endpoints for the subintervals x1 to x10. Okay, so the three things I recommend writing down the formula for it. I recommend drawing a graph of what we're doing and also creating a number line to find our delta x. Okay, so here are the three things. On the bottom, we have the Riemann sum approximation formula with 10 different subintervals here. You can see that I already factored out the delta x2 just to make it a little bit easier. On the top left, we have the graph that I didn't finish yet, and then on the right, we have the number line. So what we're going to be doing is taking this number line on this x-axis and chopping it up into 10 different subintervals. So we have 10 different subintervals in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we need to figure out those values for those subintervals, and then we're going to take the left endpoint for each one. So finding that, that's going to be delta x. So delta x is the width. We know is b minus a over n. And b minus a, that's 1 minus 0 over 10. N is 10, which is 1 over 10, which is 0.1. Typically, if you can use a decimal, it might be a little bit easier to use the decimal version. So what we're going to do is continuously add 0.1. So that's going to be 0 plus 0.1 is 0.1. Add another 0.1, add another 0.1, and you keep on adding 0.1. And for this one, it's pretty easy to add 0.1 to itself until we get to a value of 1. So these are the x1, x2, all the way to x10. We choose the left endpoint of each one. So we're choosing the left endpoints, which means the rightmost one gets left out this time. So let's go ahead and just do a quick drawing on what it would look like on here. So we have our little subintervals in there. I'm not going to label them all because it'll get too crowded. I just labeled 0.5. We're going to use the left endpoints for each one. So for this one, I'm going to start on the left. So using the left endpoint between a 0 and 0.1, that's going to be 0. So starting at 0, that's actually not even going to give us a rectangle. Next, between 0.1 and 0.2, that's going to be 0.1. So we go up to the y value and draw a rectangle. Next is between 0.2 and 0.3. So that's the left one. Go up to the function for 0.2. Next, 0.3 and 0.4. go up on the left, create a rectangle. Next one, 0.4 and 0.5 on the left. And you can probably see where this is going. So you just keep on going up to the left and creating a rectangle. And you can see that while we are doing this, this is going to result in a under approximation because it does not quite fill in every gap of the curve. Okay, so we're going to find the area of each one of those, and we're going to add them up, and that's going to give us our approximation. So let's go ahead and plug in down here what we get. So delta x was 0.1. And now f of x1 was 0. F of x2 was 0.1. And it goes all the way up to f of 0.9. Remember, we're doing left endpoints, so the rightmost endpoint does not get a function value here. So now we have to do each one of these. So I'm not going to actually go ahead and write each one in because there's a bunch of them, but you would evaluate f of 0, so 0 squared, 0.1 squared, 0.2 squared, and so on. So I'm just going to skip to what we get when we do that. So if you do the function evaluated at all of those x values, you get all of these decimals, and then we go ahead and add them all together. And we get 2.85. We multiply that by 0.1, so we get 0.285 for our approximation. Okay, so remember that the actual area here is what we found in the last one. The actual area is, from 0 to 1 here is 1/3, which is about 0.333. It's 0.3 repeating. So our area here is a little bit closer because typically the larger amount of n values you use, the larger amount of rectangles you use, the more accurate your approximation is going to be. And this drawing is incorrect. Don't look at that because that was the graph that I drew, the graph that was drawn before I switched it from right endpoint to left endpoint. So the last thing we're going to mention is actually very, very, very important, but we're not going to do too much with it. We're just going to kind of mention it, is the fundamental theorem of calculus. So anytime you hear the word fundamental theorem, you should know that it's important, and it's actually something that we kind of just mentioned. By increasing the number of sub-intervals, increasing the number of rectangles that we use for the Riemann sum approximation, it's going to be a better and better approximation. That means it's going to approach the actual area underneath the curve. Anytime you have the word approach, you should be thinking limits. So what we're going to do is we're going to rewrite this showing that the limit of the Riemann sums is equal to the definite integral of f, which is the area underneath the curve. And this is the fundamental theorem of calculus. So what we have here is if we're doing over the interval from a to b, we know this side, right? The right-hand side, the integral from a to b of f of x, that's going to tell us the area underneath the curve. And we do that by finding the integral and then plugging in upper bound minus lower bound. So now what we can show is if we have this right here, this is the Riemann sum approximation using n number of rectangles. As the number of subintervals gets larger and larger, that would mean that the distance between each x1, x2, and so on goes to 0. The limit as that width goes to 0 of that Riemann sum actually ends up equaling the area under the curve. So all this means in layman's terms is that the more and more rectangles that you use for an approximation, the better the approximation is going to be. Okay, so that is all we have for this section.